as he said, I'll be presenting work that I did as my undergraduate dissertation on hopefully improving type, highlighting systems to allow users to understand types better and debug types better. So I have a few goals. First thing, I want this to be complete in the sense that it will include all the information in the program that contributed to a type of an expression. And as a complete system like that ends up highlighting quite a lot of code in some cases, I want this also to be interactive. So you could look at a type and be, it's a huge function, loads of different arguments. This particular one didn't really make sense to me. I want to focus on that, basically. And it also works for dynamic errors as well through like cast systems or anything similar. So my main focus has been on creating like a more formal foundation for this, because I find type systems and semantics often have a lot of rigorous theory behind them, but the error systems and UI systems often not so much. And I also have a sort of in-progress implementation for Hazel, for these techniques in Hazel, which I'll demonstrate a little bit. So just to explain what Hazel is, I've got a live build that you can try out what I've got so far. And Hazel basically allows you to have holes in your programs, and it gives them the dynamic type. So it's a gradually typed system, and it's also bidirectionally typed. So all of my things only work at the moment for bidirectional typing, but it'd be interesting to see how some of it might extend to some more global constraints, because of course, as we saw before, refinement types and dependent types, their errors are absolutely horrible, but a lot of the time with inference and stuff, you can't really, you need a load of constraints as well, which this won't cover. So I'll just give a bit of an example of how this works. So if I have a if statement here, I can write some functions, like for example, here's just a function that it's given the type something to integer, and it will highlight the function itself and the body, because that's what gave the type information, but the argument didn't do anything. And then I could do just a simple tuple, everything matters here. But then, because this is going to be decomposable, we're going to be able to take just the parts of the types that actually conflict. What I can do is I can select the error here that the branches have inconsistent types. By the way, the types have been on the bottom of the screen here in the cursor inspector, which I forgot to mention. And it highlights only here the function and the tuple, not the elements inside. Equally, if I did two functions, that's consistent, so it will only highlight the bodies of the functions. And just overview on bidirectional typing in case anyone's unfamiliar. It basically splits type checking into two modes. Synthesis, which is basically you have a term and you can determine the type from the term itself and synthesize it. So for example, with this function, we can determine its argument is an integer because it's annotated, and its body is an integer because it's a plus expression. And then on the other hand, we have type analysis, which takes information from the context, from around the term. So for example, the 1 in that function is required to be an integer because it's in a plus expression. So now, what actually are this highlighting? So I'm going to be using a method of term slices or program slices, which is basically a term, and you omit parts of it, which I will notate with a question mark. You'll see the paper used squares, but I'll use question marks to be consistent with the Hazel notation, because they're effectively the same as holes in Hazel. Wrong way. And it produces, you can define a precision relation on this, saying if I omit part of a term, it's less precise. So for example, I have 1 plus 2, I can omit the 1, and then I can omit both, and they're all progressively less precise. So that, and then importantly, that corresponds with highlighting the parts that are not emitted. And what's interesting about this is such a slice is also a valid Hazel program. So you can still run it, you can still type check it. Some interesting ideas could be to do with, if you're giving it to an AI or something as well, you can give it a well-formed program to use, and it will only include parts relevant to the type that we're querying or that we're looking at. And then you can join these to retrieve the original information. Of course, only if they're actually the same sort of term. You can't join a plus term with a regular integer. So what I haven't done yet is sort of think more about the UI and usability of this stuff. So I've got a three-step process of what I think would work quite well, but this is where I'd really like some discussion on this afterwards or some questions about this. So basically, select an expression you want to look at, and then I want to, and you can then view its type in the cursor inspector. And then what I'm thinking is you can select parts of this type. So, well, you can omit parts of this type, or you can select subterms of this type to sort of focus on what you really don't understand. So imagine you have a int-to-int function, and you understand why its argument is an integer, but you don't understand why it's a function, or its return is an integer, and you'd be able to select those parts, and then it would produce a slice giving you the minimal program that contains all of the information that you're actually looking at. So just as an example, here's a is0 function. And if I look at the type down on the bottom, I can then say, well, why is it a function, and why does it have a Boolean return type? So that's equivalent to sort of omitting the integer here and taking a slice of the type. And then it would give me this. So it doesn't care about the argument because that wasn't used. And I'm also only caring about one of the branches of the if statement. It's arbitrary which one we choose there. So now I'll talk about some of the, because what I've done so far is the formal semantics of most of this. So I'll go through how this actually works. So far all I've talked about is slices of terms, and that works for synthesis because all the type information is contained within the term. But when we're taking, when we're in type analysis, the information for the type comes from outside the term. So we want to use contexts in the same way that contextual dynamics has contexts where you choose one subterm as the focus. And they can be sliced basically the same way, but you need to make sure that the focus stays in the same place, structurally speaking. And a few people have told me that the terminology can be a bit confusing here because there's also typing contexts, which I'll talk about a lot. So to avoid a clash with these sort of contexts, I'll always be calling typing contexts typing assumptions directly. So then when you type something, you also use the typing assumptions, and we want to find what are the minimum typing assumptions that we can take, that we can use to type something, and also maybe only part of the typing assumption is useful for what we're looking at. So we can also form a precision relation on this as well. So assuming x and y is more precise than assuming just x, which is more precise than assuming a less precise type, like just regular function versus integer functions. And then you can do a similar thing for contexts, because in a context you will either add more assumptions. For example, if the context contains a variable that wasn't already used, or it could remove assumptions if it binds a variable that is now, which is used in the subterm we're looking at. So they're essentially functions on typing assumptions. And you can define that point-wise. It doesn't hugely matter. So now I'm going to talk about the actual decomposable aspect of this, which I guess is the most important thing. So I'll give a very, very simple example here of, we just have a function from strings to integers. It's a bit of a stupid function, but what we want is we want to, during type checking, calculate the slices for just the argument and the body. So the argument here would be just x is a string, and then we can place it in a context that puts it sort of inside the function to get string to a unknown type. So, and then for the return for the body, we do a similar thing but omit the argument type. And then how do we actually get the thing on the bottom? We can join the two slices, which means you sort of get a structure that is indexed in the same way as types, but the only addition is we have a load of contexts here to make sure you can put the argument within the function and the body within the function and then join them afterwards. So basically reconstructible slices is what I call them. And then the way this actually interacts with querying is if I want to emit a part of a type, all I do is omit the corresponding part of the slice. And if I want to take a subterm of a type, I just take the subterm of the slice here. And if I want to show the whole thing, I join everything with this overline operator. So this leads to two main constructs: a synthesis slice, which is you have an expression, it synthesizes a type, and you will be able to take a slice of that actually contributes to the type. And it must, the resulting slice, when treated as a Hazel program, must synthesize the same type as what you're asking about it. And under this precision ordering, the whole reason I set this up is so you can find out a least precise one, and that will omit as much information as possible. So for example, this is the same is0 function from before, and it contains all the information required to determine that it's an int to int. So if I put that in Hazel, removed all the non-highlighted bits with holes, then it would synthesize int to int still. And analysis slices are the converse, where we want to take show what part of the context contributes to the type. And they're quite a bit more complicated because I've just been sort of vaguely saying the context around a term and not really defining what that is. And what it is a context which enforces a typing constraint on this term we're looking at. So there will be many of these. So in that example, we've got one annotated with an int. That imposes one to be an int. But equally, if I added another annotation to a dynamic type, it's still a checking context. And if I add a Boolean, again, it's still another valid checking context. So there's infinitely many of these. But what we care about is a minimally scoped one, i.e. no subcontext is also a checking context. And there's, again, many of those, but when we're looking at a subterm in a actual program, only one of those will match the structure of the program. So for example, here I'm highlighting the integer annotation for 1, and that's the only, if we imagine the whole thing as a program, it's the only minimally scoped checking context that will actually, that we can pick from this. And again, they're the same as synthesis slices, and we just take a slice of that context. It must impose the same type constraints as what we're querying, and the least precise one is the one we care about. So for extremely simple example, if we have 1 plus 2 as our program, the minimally scoped typing context, checking context for 1 is plus 2. And then we can omit the 2 because that doesn't contribute anything to the type here. Well, in the version of Hazel I was using before, I think there's now some sort of ad hoc polymorphism for integers and things like that. Not sure about that. And then for how this works with dynamic casts or any dynamic types, basically, because all of the slice information is decomposable in the same way that types are, we can basically just tag it onto types and pass it throughout evaluation in the same way that the casts are treated, which allows us to debug things like type errors. So if I create a dynamic function for addition, adding 1 to string of 1, it's not caught at compile time because these are all dynamic types here. But when we evaluate it, I can select int, and it will give me the slice that determined that that expression was an integer. And so it kind of tells you where this went wrong. So for further work, I really want to improve this UI, basically. And how can we exploit the decomposable nature of these slices to sort of allow people to interactively explore what they're doing. There's a lot of things that you feel like you might want to omit from slices, but the mathematics kind of requires them to be there in order for it to be a well-formed program. So it'd be interesting to see what bits might be useful to omit, even omit in practice, even though you would have them behind the scenes. So this could be things like let bindings. I also want to mechanize my proofs because at the moment they're all sort of a bit hand-wavy. And the implementation sort of partially works for polymorphism and recursive types, but the meta theory needs a bit of extending for that. And there's also some pretty difficult issues when you have type eliminators. So if you have a function, say from int to int, and you apply it to an argument of int, then the resulting type will be an int, but there's a lot of information that went into determining that. So the slice will not be decomposable because that's based on, it's indexed based on types, and the type is atomic. So I'll show that. If we have a function here, it's an int to int identity function. We can apply it to a integer, and we'll see that it highlights the function and the binding, and that it's being applied. And we'll find that basically, literally, well, almost everything here is highlighted, but I wouldn't be able to look at this in any sort of interactive way because it's just an integer. I can't do anything with that. It's an atomic type. Oops, wrong slide. Anyway, that's all, by the way. Thank you.
Okay, thank you. If there are questions, people can come to the microphone. While people are thinking about their questions, I'll just remark, you didn't really dwell on this limitation, but there's no support for liquid types in this language because, of course, the language Hazel is a language with holes, and the liquid types would leak right out through the holes. So, okay, go ahead.
So I think I might have missed the initial motivation. So I see these mostly for students who are getting into functional programming, or do you think this would also?
It could be, yes. It could also just be useful for very quickly or more quickly debugging errors where instead of it just saying these are the two, these types are inconsistent, it will actually show you where the inconsistency came from. So just, for example, this here, it's highlighted the two conflicting terms. Very obviously this is a very simple example.
So in this case, I would never write it like this with the function inside both branches, right?
Yeah.
You could have some kind of linter, or the famous, if it has more than 4 lines in Haskell, it's wrong. So I think there are other alternatives to do that, but I actually see this very valuable in teaching functional programming, especially in the case of unification. And is that the part that you don't support yet in the current work, the last point?
Yes, so that's what I'd really like to look at to see if I could make it work for unification or constraints and things like that, but it's I guess, significantly more difficult to work with.
Because I think you need global information and to store the equations and something like that. But I would be interested in having that, and that would be a first step towards something like liquid types. Thank you.
Okay, so just to prove to you all that I'm capable of asking actual questions, I want to ask about design language. So, when we present things to users, there's a language of symbols that we use. That you can think of it as sort of like a layer on top of the actual programming language, right? So, the a green symbol should mean the same thing as another. Like if a symbol is green, then the greenness should mean something, and then when you see green somewhere else, it should mean the same thing. You have a fairly sophisticated visual language with different shapes of delimiters, different colors and lines of different shapes. Can you talk about your process for designing that language, that sort of visual nomenclature, and how you think you might go about evaluating it?
Do you mean with Hazel or the...
Well, I think you have a layer on top of Hazel, right, in terms of how you're showing the type inference process, right? You're turning this into, if you can go back to, it was toward the end of your talk, you have, maybe it's slide 18? No. Yeah, they're here, okay. Okay. So, you've got this shape, and this shape, and this shape, and there's a circle, and then sometimes you have, there's a bracket that doesn't match because you're trying to emphasize. So, can you talk about that?
So, the Hazel UI stuff was not made by me at all. So all the highlighting on the left side, I've basically just reused how that system highlights terms, and I just gave it green because green was already there in the code. So I just wanted to be different to red because, of course, red is what they use for the other errors. And it is probably worth talking about how in a lot of these I've been highlighting selecting terms like this. So I've selected the function there. And that in the current UI for Hazel, that doesn't actually really select a term. It's kind of more just selecting text. The selected term is actually determined by where the red cursor is, so that's the whole function. So I couldn't, for example, select part of a term. So I can select an incomplete term like this in orange, but what's actually being selected is the red line, and I feel like it would be interesting to try and come up with a way that allows you to select with just scrolling rather than just where the cursor is, because especially if I was trying to, this is of course the bit that's not implemented, I can't click on these parts of the type to work out what's that part of the slice, but that would be very useful to have. As for the circles and question marks, I used question mark to be consistent with Hazel holes, which I can just write question mark here. And the circles was to distinguish from squares, which I have in the paper.
Okay. Is your question short?
Sure.
Okay.
It's more for my own understanding. So I believe slide 15, if you go there, this was showing the slice of how you understand the function goes from integer to Boolean.
Yep.
It seems strange that the true is not highlighted, but the if, then, and else are. Right, like those are a lot of highlights to determine something that is in like tail position, which should just be the true and false. Like, so I guess my question is, why is the if and then and else highlighted in this sense and not just true and false?
Yeah, so that's sort of, that's quite an interesting question, and I've heard a few people say similar things, but it's because the fundamental system is I want to produce a slice, i.e. a valid program that you could still run, for example. So if I just omit the Boolean.
So everything that's not highlighted, I could put a hole there.
Yes.
And it would still run.
It would still run, and it would still type check. You could still do all of any sort of analysis on that.
Okay.
So if I omitted the if statement, of course, it would not be well formed anymore. Well, actually, it would be well formed.
Well, it would, like if the whole expression was gone and there's a hole, it would still be.
Yeah,
well
but then it wouldn't synthesize the Boolean result.
Okay, so the true isn't there because you only need one.
Yeah.
And the false you would
So
need
I could have
another
highlighted true and not highlighted false, for example. And they're both valid minimums. It would be useful from a user perspective to maybe pick the one that has the least amount of terms.
Okay.
And
Yeah.
probably be
I have more
easy.
questions, but I'll ask after.
Yeah.
Thanks.
Okay.
Okay, let's have one more round of applause.